Hey everybody, welcome back to another round of physics, and yeah, let's get going. As the title would suggest, we are today going to introduce and discuss Coulomb's law. And before we do that, I have to take you back down memory lane. That is, to review some stuff that we have previously done in presumably other iterations of the class. And that is gravity. Now you'll notice straight away, I'm not talking about the near Earth approximation to gravity. You say, oh, I know the gravitational force, it's F equals mg. That is not the force that we're talking about here. We want the full-blown definition of gravity, if you will, the Newton's law of gravity. And so I have that displayed for you here, namely the gravitational constant g, m1, m2, and then we have the r squared and the vector r. And the thing that I want to jog your memory about, threefold, first of all, that this g right here is a constant, right? It is 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. Okay? That's the first thing. The second thing that I want to remind you of is, what does this r represent? And you notice that I tend to use the subscript r12 or r21 just to remind myself when I see the equation. And the idea here is that it is the relative distance between masses 1 and masses 2. Presumably, somewhere you'll have a coordinate system, we'll say y and x, and an origin, right? And then once you establish or agree upon a coordinate system and an origin, then you can have position vectors that point to the position of object 1 and object 2 with respect to the origin that you have chosen. Okay? And those vectors are what I refer to as position vectors. Okay? Now here's the trick, is that r21, what I have drawn here, is the vector, the position of 2 with respect to object 1. In other words, and I'll do it in a different color here for us, starting on object 1, r21 is this blue vector, the relative position vector. Now, I'll leave it to you to look at it graphically, but you should be able to write out an equation that relates the position vector of object 1, the position vector of object 2, and then the relative position vector between those two objects. So if you don't see it right away, go ahead, pause the video, take a minute, and see if you know that answer. Okay? Good, good, good. And I would encourage you, think about how to graphically add vectors. But here we see that if I take the position vector of object 1, I add to it the relative position vector, I should result in the position vector of object 2. And so by following our rules of algebra, we see that the relative position vector between the two objects is simply the position vector of object 2 minus the position vector of object 1. Okay? Good. Okay. So that takes care, of course, once we have the relative position vector, finding the magnitude simply involves applying the Pythagorean theorem. Now again, if you don't remember that, I'd say go back, review your vector, your basic vector algebra, and we recognize that the Pythagorean theorem is the way that we calculate the length of a vector. Namely, we take the x component and square it, we take the y component and square it, we take, if there exists, the z component, square it, we take the square root, and that tells us how to calculate a magnitude. Okay? So once we have the relative position vector, we apply our ideas about magnitude, and that is the number that goes in the denominator of Newton's law of gravity. Good so far? Sweet. Good. Well, we have one more thing that we have to deal with. Well, maybe two. Now we have R12. I'm going to go ahead and erase this information for clarity of our image. But you notice that the relative position vector starting on object 1 and pointing to object 2, it's in this direction. Okay. Now the next question, what happens, we have a hat notation here. Okay. What does that actually mean? And that's reserved notation. That is a notation that has a very specific meaning in physics. Yeah, good. Anytime you see a hat, it represents a unit vector. And the unit vectors are very important because they have a magnitude of 1. So anytime you see a unit vector without any kind of calculations, you immediately know that the magnitude of that vector is 1. Now, how we usually describe this in physics is that we think of unit vectors as showing the direction that a particular vector is pointing. And then we take that unit vector and we multiply by some magnitude in order to express the entire vector. Looking at Newton's law of gravity, we see that we have a unit vector which gives the direction of the gravitational force. And then you could think of the strength or the magnitude of the gravitational force as being determined by this scalar coefficient out in front. Okay? Good. Well, there is a question that's lingering here. If I know the vector, the relative position vector, how can I figure out a unit vector associated, a unit vector that is pointing in the same direction but has a magnitude of only 1? And the example I would give you, I would say, hey, what happens if I give you a vector that's, 10 units in length? We'll say that this vector is 10 units in length. How would you turn that into a unit vector? Yeah, good. You'd say, I'll just take 1/10 of it. So the unit vector would simply be the vector r divided by 10. Okay, I buy it. Well, what happens if instead I make this vector, I don't know, let's say that it's only 0.25, a quarter in the x direction. Yeah, you say, wait a minute. Well, you might either say, multiply by 4, and that will give me my unit vector. Or an alternative way to be thinking about that is you take your vector and I divide by 1/4. And that would also give me the unit vector. Yeah. And so you can see the pattern. Let's go ahead. That's just with specific numbers. But now let's go ahead and generalize more formally. If I have a vector, all I simply need to do is divide by the magnitude of the vector, and that will turn it into a unit vector. No problem. So if I have the relative position vector, I can go ahead and divide by the magnitude of the relative position vector, and that will go ahead and give me the unit vector. And that's perfectly general. You can do this with, I'm using this example, but that's perfectly general for any vector that you're given. Okay? Pretty cool. It also helps because we had to, bumped the table there. We had to find the magnitude of that vector anyway in order to apply Newton's law of gravity in the first place. So we have that piece of information and we're just simply going to use it to find the unit vector. So now we have some idea about the unit vector that points from object 1 to object 2. Okay. And notice I've just used my rules of vectors. I have just simply translated that vector to a new location on the slide. Okay. That doesn't change the properties of the vector. I'm allowed to translate it without penalty. Okay. The last thing that I should point out is what is the purpose of that negative sign? When I have a vector and I multiply by a negative sign, what does that do? Yeah, very good. It flips the direction of the vector. Okay? So if the relative position vector is pointing in the, we'll call that the 2 o'clock position, it's pointing diagonally to the upper right, then a negative sign will cause that vector to flip, and so the negative r2 1 hat is pointing not away from the first mass, but towards it. Okay. Right? Good so far? Yeah. And so you notice that, I'll go ahead and I'm going to get rid of this stuff now for sake of clarity. You notice that the gravitational force of object 1 on object 2 is such that object 2 is pulled towards object 1. So oftentimes when you're dealing with Newton's law of gravity, you'll hear people say, oh, the negative sign means that gravity is always attractive. It pulls the two objects together. Okay. Of course, if I went ahead and I said, well, what's the gravitational force of object 2 on object 1? And we go through and do the same rigmarole, we'll find that the unit vector is pulling object 1 towards object 2. So that's the purpose of that negative sign. Very important. Sweet. Yeah. Well, let's go ahead to the topic of the day. And now that we have our brains refreshed for Newton's law of gravity, introducing Coulomb's law will require just a couple of slight modifications. So let's go ahead and look at those. First off, I'll say here, I've written down gravitational force and the Coulomb force. And you'll notice some very similar ideas straight off. Both of them have a relative position vector squared in the denominator. And usually what we refer to Coulomb's law or the gravitational force law, we refer to those as inverse square laws. They depend on the square of the distance between the two objects. Now the objects I've labeled 1 and 2 in both equations, but when we're dealing with gravity, the interesting physical property of the objects are the mass. For Coulomb's law, the interesting physical properties of those objects are the charges. So we replace m, which we reserve for mass, with q. And generally, q is reserved in physics to represent the charge of the object. So that's the first change that we see, is the m's become the q's. Another change that you notice is that no longer do we have the gravitational constant, g, but we have what's appropriately named or creatively named the Coulomb constant, k, right here. Okay? And that's generally referred to as the Coulomb constant. You say, where do they come from? It seems that these are numbers that nature just simply uses. You could say, well, where does pi come from? Or where does the speed of light come from? Where does the charge of an electron come from? These are just numbers that seem to be the universal constants of nature. Now, one thing I will point out to you is that gravity, the constant is 10 to the negative 11th, whereas the Coulomb constant is 10 to the 9th. That represents a difference of 20 orders of magnitude. So that's why you generally hear that the force between charges is much stronger than the force between two masses. It's because of that idea sitting there. Good? Another point that I'll have to make very quickly is you will sometimes see Coulomb's constant written in two different ways. Some books will just simply use the constant K. Other books, I believe the one that we're using in our class, will write it as 4 pi over epsilon naught. Okay, so epsilon naught, that's what that is. And that is sometimes also, well, I shouldn't say sometimes, it is the permittivity of free space. Free space. Okay. And that little number will come back into play, but for right now, it's okay to just have Coulomb's constant 9 times 10 to the 9th, that whole thing. Okay. You could say, well, why does that even exist? To be continued when we start our discussion about light. Stay tuned. Okay. As I've already mentioned, I believe the next one I'm slightly out of order. Oh, inverse square laws. Okay. Okay. Now, one of the things that's really important, one of the distinctions, is you'll notice that there isn't a negative sign in Coulomb's law. Okay. And that is because, unlike gravity, which is always attractive, Coulomb's law, the interaction between charges, can be attractive or can be repulsive. In particular, you know that if you have a positive charge and a positive charge, and you put them close together, they will want to repel one another. Well, a positive times a positive gives me a positive. And so within Coulomb's law, a positive charge and a positive charge will end up with a positive value at the end of the day. And so that causes those charges to force away. That's, I should say, mathematically how we express the physical result that the two are repelling. Conversely, if you have opposite charges, a positive charge and a negative charge, from the mathematical standpoint, when we multiply those two together, we end up with a negative value, and that negative value has a physical interpretation of attracting the two together. So Coulomb's law has that built in, the attractiveness and the repulsion all in one. Pretty cool. Now, not to cut this lecture short, but that's basically all we really have to do, because we've spent an entire chapter dealing with different types of forces. For example, the gravitational force close to Earth, or the frictional forces. Maybe you say, well, wait a minute, there's some nastier ones. Yeah, indeed, like the spring force, or maybe like air drag, or, I don't know, law of gravity. Like, for example, tension or the normal force. But you have worked an entire term on how to analyze problems from the standpoint of forces. You're hit with the forces problem. Generally, one of the first things you do is you identify a system and surroundings so that you can go ahead and apply something like Newton's second law, whether it be for constant masses or if you want the more generalized form dealing with changes in momentum. Okay? So in some sense, I say, well, you already know how to use Coulomb's law because you're going to go into Newton's second law problems. So we just have an extra equation to add to this ever-growing list of interactions that we have previously dealt with. There. So that's about all I have to say in terms of actual content, but now we just simply get an idea about, hey, how do we practice this? Okay, so for example, there's already an electroscope problem if you want, just to run you through that. And of course, bring your questions to class. We'll get some extra problems prepared and we'll just go at it. So, well, that's all I have for right now. Thanks for your attention. Keep up the good work. I'll see you next time.